halfway through, and hopefully that feels good. I think first semester is harder than second semester because in second semester, while we have maybe a couple labs that might be a little bit more challenging, um, once we get, as we start working more and more with moles and stoichiometry, it's kind of what we're going to be doing for the rest of the year, but just applying it to different circumstances. So, yeah, we we have class today, and then for your homework this week, we have we have just to finish that semester review worksheet and to take the semester test. There is something called the coffee and gas exercise also. It's an assignment. It is not due until the 12th of January, but it is a fun mini unit on organic chemistry. And so it is due, and I would recommend just getting it done. It's a little bit longer. There's some reading, and it's kind of just, but it's not hard. Okay, it's just gives you guys the a little touch point of organic chemistry. And organic chemistry is just a really fun class. If you guys go into college chemistry, organic chemistry is one of those classes where you get to go into the lab, and the labs are like 3 hours long, and you go in there and you're trying to make, you know, acetyl acetate, which smells like pear, or maybe you're making Tylenol in the lab, and so you kind of have these fun um, opportunities to synthesize stuff that we use on a daily basis. Maybe not on a daily basis. Maybe you're not using the pear extract on a daily, but or maybe you take Tylenol every, once a week or not at all. Who knows? But I do think organic chemistry is probably one of the funnest classes. It's also notoriously one of the hardest classes, but I don't think it's, looking back on it, I'm like, I probably could have enjoyed it more because, when you're 20 taking those classes, it's a lot different than looking back and going, oh, probably wasn't as hard as I thought it was. So, all right, who got the word of the day today? Anybody? Eli, go ahead and type it in the box. Convert. All right, so when we think about stoichiometry, really, it's just molar conversions, pretty much all around. That's what, I can hide this now because we're done with our fireplace and Christmas music, aren't we? Stoichiometry is basically setting up a long conversion line and converting to get to what you want to get to. So that's what stoichiometry is. And we're going to talk about that for a little bit today. Then we'll do a short review. Kind of, some of you have probably already started working on the semester worksheet. And so I'll take any questions, and we will kind of go through some of those problems if you'd like. And then at the end, we'll do a breakout. And you guys, this is my, I don't know if you can see there's my ugly sweater. It's just says Merry Christmas on it. Hopefully you guys are having hot cocoa and are wearing your ugly sweater. You can come on camera and you guys can solve some riddles and some problem, like they're like little puzzles, Christmas games in the breakout rooms. All right, let's see. Let's get started. And are there any questions? Cookie and Mole Lab, everybody cooked their cookies and their recipe worked out, hopefully. I really should have it so it's like you have to follow your recipe to see if your recipe actually works out and you actually get decent cookies. They were good cookies. That's good to know. I made them once, maybe twice, probably most likely once because my son probably didn't do the lab. My daughter did though. Too much butter. That's okay. They were flat. All right, so if we have flat cookies, now you guys can go back to your discussion, and you can look and say, well, how do I make a more cake like cookie? How do I make a more chewy cookie versus a crunchy cookie? And so that's kind of the point, is get you to think about kitchen chemistry, because chemistry is not just in the lab, it's in your kitchen. And it's interesting to think that there's professional pastry chefs and bakers and cooks out there that know exactly how to reduce something, when to turn off the heat. I mean, they are chemists in the kitchen, and to make the right reduction of a sauce, or to make the cookie rise just the right amount. Um, our The lady who did my daughter's, well, we've been using her for years. She bakes cookies and does like those fancy designs on them and stuff like that. She did our wedding cakes for my daughter's wedding, and she's also done our birthday cakes and stuff like that, and graduation parties, all of that stuff. But she messed up one time, but it made the cake a little bit denser, and everybody was like, "Oh my goodness, this is the best cake ever," because it was moist. It was cake, still cake-like, but it was just a little bit more dense than like a light and fluffy cake, which I don't really like the light and fluffy cakes. I like mine are a little bit more dense. But with this raspberry jam in the center and cream cheese frosting, it was probably one of the best cakes. I'm like, Shelby, can you please replicate what you did that one time? She's like, I don't even remember how I messed it up to make it taste so good. But anyways, we she keeps trying, and she always makes it taste good. So anywho, my little side story. There's my squirrel story for the morning. All right. We ended last week talking about mass percent composition. Okay, that's what your worksheet was on. And basically, it's taking the total mass of an element present and dividing it by the total molecular mass. Pretty straightforward. If you have 13, or let's say 15 red or 15 beads, 5 are red, 5 are blue, 5 are yellow, 5 out of the 15 are red, and that would be 33%, right? One third. Um, and so that's really what we're doing. That's it, but they're doing it by mass. And so you take the mass of each element present, and if you have more than one atom, you have to consider that, divided by the total molecular mass, and you get something called mass percent, which sometimes you'll see written as, get my pen working, right here, weight over weight, W over W. That's a mass percent. Sometimes you'll see like a, what is it? It's mass and then density, or you'll see like a liquid or something like that. So we'll see different uh, what am I abbreviations. That's the word right there. I had to read it. Abbreviations for different things. But usually it's just when you have a percentage, you're dropping the units. So this is unitless, and it's just the percentage. It can also be used for finding ppm. Does anybody know what ppm stands for? Yeah, parts per million. And this is sometimes you'll also say not B, ppb. That would be parts per billion. And you'll see this when you're talking about environmental contaminants. Environmental contaminants. Maybe you're going to get your water tested, your well water, or your city water. Sometimes they'll have, lead. My goodness. Lead or arsenic, and they have like a maximum number that you can have that's acceptable in your drinking water. So I don't know what the numbers are, but the EPA, Environmental Protection Agency, gives us ranges that are acceptable for us to ingest on a daily basis. Okay. Now, when I was working at Georgia Pacific, kind of if you guys ever use toilet paper, Charmin, they make Charmin toilet paper. And I was working as a chemist there. And we were allowed, and this is part of the process of making paper. There's bleach, there's contaminants that are put into the wastewater, and then as an environmental chemist you would go and you would sample the water that's being processed and leaving the plant, and you would sample that water, and we were allowed so much waste, right, from the chemical process allowed to go into the ocean or the rivers and stuff like that. So, and the EPA sets those, and you get fined if you're over. But the whole point of being like in the lab is monitoring the process so that nothing goes into the water. Or into the air or into the ground or whatever. But that's why you have the environmental engineers that are running the process, making sure that everything is above board. And then we have the environmental chemists that are testing and process samples. And so, yeah, you had to collect morning and night, and you had to run samples, and sometimes they would do overnight samples and whatnot. So pretty interesting how that all works. And that all has to do with your parts per million, your mass percent composition, your percent of what you're putting into the wastewater, into the air, or whatever. So I think you guys understand most of this, but you have a pizza, one whole pizza, 2 slices are pineapple, 6 slices are pepperoni, and 4 slices are cheese. How many total slices do we have? 12. And so what percentage of the pizza is pineapple? We would say 2 divided by 12 is 1/6, or whatever the math is there. Not 6%. Is 2 divided by 12? 16.7%. Okay, and then 6 slices of pepperoni, that would be, Caleb, you got to try it. You got to go pepperoni and pineapple. It is with mushrooms. It's just really the best. That's right. Jonathan, 50%. And then we have 4 slices of cheese pizza, which would be, what is that, 33.3%, right? And then we look at our percentages just kind of as a way to look at it and go, okay, does this make sense? And I think that's always a good question for you guys to ask. When you solve a problem, does this make sense? If I look at this and I say, well, a whole pizza is 100%, so 12 slices is 100%. Okay, so I have 16.7% plus 50% plus 33.3%. That totals 100%. So yes, this does make sense. Obviously, it gets a little bit more complicated. It's always easy when we look at food, right? But when we go into, it's like the same concepts, but as soon as we go to the periodic table, all of a sudden we're like, okay, I freeze. So where else do we see percent composition? Clothing, copper coins, food, mineral composition. Like if you guys were to look at your labels on your clothes right now, you might see that it's, 45% cotton and 55% polyester. Okay, this is a plastic, just to let you guys know. You're just putting plastic on your skin. You might as well just go put saran wrap. I'm just kidding. I have polyester clothes, but it's not good for you. But try to go cotton or linen, wool, natural products on your skin. Your skin is your largest organ, so take care of it, right? Food, obviously there's fat percent, there's carbohydrate percent, there's protein percent, um, and whatnot. Okay, so all of those things you can look at your medicine cat, your vitamins and stuff like that. That's all percent composition. All right, so let's do a practice problem really quick. A dandruff shampoo contains dipyrithione. What? That's a big word. Um, Dipyrithione. When you have this thio right here, that means you're going to have a sulfur. Okay, just like we had hydroxy, right, or hydroxyl. That's going to be an OH. A thiol with this thigh, that's going to be an SH. Now remember, um, these O and the S are in the same family on the periodic table right here. All right, so we have a hydroxyl and a thiol. All right, these hydroxyls, this isn't what we would find on alcohols. Okay, so whether you use rubbing alcohol in your kitchen or if you're swigging back alcohol, which I hope you're not, those are going to have OHs on them. Okay, but dipyrithione is an antibacterial and antifungal agent. So we want to say, what is the molar mass of this chemical formula right here? To solve for the molar mass, Eli has it at 463. We could probably add a few significant figures there, but we have carbon at 12.01 times 10. We have hydrogen at 1.01 times 8. Okay, we have 8 of them, we have 10 of them. We have nitrogen, we have, what is that, 14.01? Yep. Times 2. We have oxygen, which is 16.00 times 2. And we have sulfur, which is what, 32.06 times 2. And then we add, we multiply and add those all up. And if we can get a more exact number, that might be better. But we don't necessarily need it. We just can because we have these extra significant figures. So if you guys grab your calculator and add this up and do the math alongside with me. So 1.01 times 8 plus 14.01 times 2 plus 16.00 times 2 plus 32.06 times 2. I get a total of 252.32. Eli, I'm not sure where you got 463 right now. Grams per mole. Let me know if you guys are close to that number. Let's get a few more people putting their answers in. Jonathan has 252.298. So he has a couple more precise significant figures. He goes out to 3 decimal points. So I rounded a few. You could have done 1.008 for the hydrogen. And I think the sulfur can go out an extra one or not, but we'll run with that. So what is the mass percentage of carbon? So we have to look at this and we say, well, here's our total molar mass. Okay, now what's the total mass of carbon? Remember we had 10 times 12.01, so that's going to be 120.10, right? Grams per mole for our total mass of 10 carbons. So To figure out the mass percentage of carbon, we would say 120.10 divided by 252.32. Both of these are grams per mole, so I'm just going to drop that and I'm going to multiply this by 100 to get my percentage. So what is my percent composition of carbon in this molecule? 47.6. Now, totally good answer. 3 significant figures is usually a solid way to look at things. And honestly, we are limited right here by 3 significant figures. Had I done 1.008, this is 4 significant figures. And if I would have done 1.008 for all of my hydrogens, it would have changed this number a little bit. I could have done 4 significant figures. But I am limited right here by this small little number right here to make it so that I am limited to 3 significant figures. All right. So how many atoms of carbon are in 25 grams of dipyrithione? So if I'm in grams, this is something you're going to hear me say all next semester. If I have grams, the very first thing I have to do is I have to get it into moles. Okay, so anytime you see something in grams in your starting problem, condition yourself to say, if I have grams, I have to get it to moles. How do I go from grams to moles? I need to know the molar mass. So for this one, I start with my given, which is 25.0 grams, and I'm just going to say DIP for short. Now I draw my conversion line, and I need to get it into moles. So 1 mole of dipyrithione is going to be what? How many grams? We already did this. Your total molar mass is grams per 1 mole. So 1 mole of dipyrithione is going to be 252.32 grams. Now notice I started with 25 grams, I did my conversion, and my grams are canceled, and now I'm in moles. But there's more to this because I want to know how many atoms of carbon are specifically in this molecule. So how do I figure that out? 1 mole of dipyrithione, let's do this, is 6.02 times 10 to the 23rd atoms. Are we done? Are we done? We know how many atoms of dipyrithione we have, but how many atoms of carbon do we have? There are 10 carbon atoms. So there are atoms of dipyrithione. There are 10 carbon atoms per every one molecule. And I shouldn't say atoms over here. This should say molecules because it's a mole of dipyrithione, right? So there are 10 carbons per 1 molecule of dipyrithione. Does everybody follow that conversion line? So I'm starting with what I'm given. I convert it to moles because that's always going to be my first step. And then I say 1 mole of dipyrithione is 6.02 times 10 to the 23rd molecules of that, because there's a mole of those molecules. Now, for every molecule, I have 10 carbons per molecule. So now we do our calculation. We grab our calculator. We say 25 divided by 252.32. We'll just go delete. We'll say enter. I'm going to carry that number, and I go times 6.02 second e to the 23, which is going to give me a big number. And then I multiply that by 10 and gives me an even bigger number. And I get 5.96 times 10 to the 23rd atoms of carbon in 25 grams of dipyrithione. Okay, so what I'm trying to implore you guys to recognize is you might not know how much information you have in that one statement. You have 25 grams of this dipyrithione, and you're like, I don't know what that means. Well, you always can start, and then obviously we were given the chemical formula. So if you're given the chemical formula, you can find the total molar mass. Once you find the molar mass, you go from grams into moles. And then we know by Avogadro's number that every mole contains 6.02 times 10 to the 23rd, whatever, atoms, molecules, donuts, whatever it may be, right? 1 mole is always 6.02 times 10 to the 23rd. But then there was one more step that we had to consider, is the fact that each one of those molecules of dipyrithione, it has 10 carbons in it. So when it fully decomposes, you're going to be left with 10 carbon atoms per molecule. You're going to be left with 8 hydrogen atoms per molecule, and so on and so forth. Okay. So, percent composition of a compound of a chemical formula. We've already looked at this. We know how to do this. Just remember this. And percent composition of CO2. I'm going to skip this because I feel like it's like beating a dead horse. If you are still having trouble determining percent composition, please come and schedule an office hour with me for the sake of time. I want to be able to get to the game at the end and stuff like that. But again, molar mass of each element divided by the molar mass of the compound. Okay. Now, what if we have only experimental data rather than me telling you what the, find the percent composition of each element? What if we have experimental data? What do we do with that? It's like, okay, well, how do we figure this out? So in the lab, I can say, well, a lab sample contains, I'm able to determine that it's 24.02 grams of carbon and 64 grams of oxygen. Now, maybe I figured that out because I was able to run it through some sort of chemical equipment, and that's what I ended up getting with some known material. So, again, we can determine some percent composition just by these numbers. And I'm going to keep it in this one because I'm still doing percent composition. I'm still going to keep it in grams. I'm not going to convert it to moles at this point. But what I can do is I can say, well, what is my total mass? And I have my percent of, or my grams of carbon. So in this case, I would go, total mass is 88.02 grams. Percent carbon is going to be the grams of carbon that I have in the lab sample divided by the total mass that I have in my lab sample. Very similar, right? I'm not really changing anything. I was just given different information, right? I'm saying my sample contains this many grams of carbon and this many grams of oxygen. And so here is what I have percentage-wise of carbon and oxygen from my lab sample. So it looks a little bit different, but I still am able to get these percentages. Okay, so that's where we're going to leave it for now, because when we come back in the new year, we're going to look at this again. And based on our lab samples and the masses of our elements, whether we have grams or moles, what we're going to do is we're going to calculate because it's not numbers, but we're going to determine what the formula could be based on the percent composition. So we're going to take it one step further and go, we're going to say, well, here's the percent composition, but now what could my chemical formula be? What really do I have? And, basically, if something is 27.929% and 72.71%, I'm going to take that information and I'm going to figure out what the chemical formula is by going through a couple different steps. Don't worry about it now. We'll come back to that. Okay, so let's look at stoichiometry. We're going to go back to food for a few minutes, okay, because everyone here hopefully has made a grilled cheese sandwich or some sort of a peanut butter sandwich. So stoichiometry is the relationship between relative quantities of substances taking part in a reaction or forming a compound, typically a ratio of whole number integers. So here, when we're making a grilled cheese sandwich, we have 2 slices of bread. It's like balancing chemical equations. 2 slices of bread, 1 slice of cheese makes 1 sandwich. So the ratio here is 2 to 1 to 1. Balancing a chemical equation, we've kind of seen this a little bit. Now, if I want to make 7 grilled cheese sandwiches, here's my given 7 sandwiches. My conversion is looking at the number of pieces of bread I need per sandwich. So here's my conversion, 2 to 1. And that tells me that I would need 14 pieces of bread. Obviously, it's a little bit easier when we're looking at food. All right. We'll just jump into model 1, a chemical reaction. Let's look at here. We have nitrogen gas reacting with 3 hydrogen gas, forming 2 ammonia gases. What is the ratio? Go ahead and type this in the box. What is the ratio of these 3 molecules in this chemical reaction? Just write as a ratio, what to what to what? What to what to what? Okay, put numbers where they belong. What is the ratio of these molecules in this chemical equation? Give me the numerical ratio of these elements. Yeah, I would, it's nitrogen, two nitrogens, 3 hydrogen gases to 2 ammonia gases. So I'm just going to drop everything and say 1 to 3 to 2. Okay. So, and what we're looking at is we're looking at what are the coefficients. The coefficients give us that number. So what are the coefficients for each of the following substances in the reaction? We have 1 nitrogen, we have 3 hydrogen gases, and we have 2 ammonias. Okay. So it says draw particle models to illustrate the reaction in model 1. So I'm going to do this for you. When I say particle models, I'm kind of talking like a Lewis dot structure. So we're going to draw our nitrogen is going to be in with a triple bond. Nitrogen gas has a triple bond. It's very stable, and it has these two extra lone pairs on the ends. Okay. Now we need hydrogen. We have 3 hydrogen gases. So I'm going to draw my hydrogens. They just each have 1 electron, and they share those electrons. And then on the product side, we get ammonia. Now remember, ammonia, we put the single atom in the center. It has a lone pair, and then it has 3 hydrogens. Okay, there's our Lewis dot structure for ammonia. So what we're looking at here is we say 1 nitrogen reacts with 3 hydrogens to form 1 molecule of ammonia. And then we have what color do I want to use? It's kind of there. Here's our other ammonia reacting with our other 3 hydrogens to form our other molecule. Okay, so that's what a particle model looks like. And you can see all of the atoms are reacting and turning it in, but you need to have 1 nitrogen and reacting with 3 hydrogens to form these 2 ammonia molecules. So the next step that we're going to talk about is this word called mole ratios. When you're looking at a chemical equation, you can say, well, what are the molar ratios of all the elements? And basically, it's comparing all of these things. So basically, I'm going to compare this to the hydrogen. I'm going to compare this to the ammonia. And then I'm going to compare the hydrogen to the ammonia. And that gives me 3 different molar ratios. So the molar ratios, I could say 1 for this chemical reaction. So 1 mole of nitrogen gas, the ratio between nitrogen gas and hydrogen gas would be 1 mole to 3 moles of hydrogen. I can also write 1 mole of nitrogen gas to 2 moles of ammonia. What is the final molar ratio in this chemical equation, this chemical reaction? There's 1 more. Go ahead and type that in the box. What is that last molar ratio? Okay, is it what's the ratio, Lexi, between hydrogen and ammonia? Is it 1 hydrogen to 2 ammonias? We have to look at those coefficients. Yeah, it's going to be 3 moles of hydrogen to 2 moles of ammonia. Those are the molar ratios. Now, I could have written this as 3/1 if I wanted to swap it, like 3 moles of hydrogen to 1 mole of nitrogen, depending on what is on top and what is on bottom. Okay, so you could flip these around and also say that this one is 2 moles of ammonia to 1 mole of nitrogen. Okay, those are the same conversion, same ratio. One is just, it just depends what you have on top and what you have on bottom. Does that make sense for what molar ratios are? You have to balance the chemical reaction first, and then you look at the coefficients in front of the uh, molecules in the chemical reaction. So you're looking at the coefficients, and those coefficients tell us what the molar ratios are between the different molecules in the reaction. All right, so let's look at this again. This hopefully will help you understand the concept of what a mole is. So for one single reaction, how many molecules of each substance would be consumed or produced? Okay, how many molecules of nitrogen in this reaction are consumed? Go ahead and type that in. And it's for one reaction. How many molecules of ammonia are in the reactants? One. Okay, for a single reaction, how many hydrogens are consumed? How many molecules of hydrogen? Yeah, 3. For a single reaction of 1 nitrogen and 3 hydrogens, how many ammonias are produced? That's right. That's that same ratio that we were talking about. All right, so the ratio here is still going to be 1 to 2. I'm sorry, 1 to 3 to 2. Now, let's look at it a little bit bigger. If the reaction occurred 100 times, how many molecules are consumed or produced? So how many if this reaction occurs 100 times rather than just one time, how many molecules of nitrogen need to be consumed? Yeah, good job. 100. All right. How many molecules of hydrogen in a reaction in a reaction occurring 100 times? That would be 300. And how many ammonia are produced if the reaction occurs 100 times? 200. Now, what's the ratio of this? Reduced. It's still 1 to 3 to 2. Okay, let's go even bigger. If the reaction occurs 6.02 times 10 to the 23rd times, how many molecules of ammonia of nitrogen are used in this reaction? If the reaction occurs 6.02 times 10 to the 23rd times, how many molecules of nitrogen do I need? That's right, 6.02 times 10 to the 23rd molecules of ammonia. All right. If the reaction occurs 6.02 times 10 to the 23rd times, how many molecules of hydrogen do I need? I'm just going to put a 3 here, times. And maybe for short, you guys can, instead of writing out 6.02 times 10 to the 23rd, we can just go Avogadro's number, a pound. That would be a nice shorthand way of saying Avogadro's number, right? Yeah. This number right here is Avogadro's. So if the reaction occurs that many times, I would need 3 times Avogadro's number. All right. So if the reaction occurs 6.02 times 10 to the 23rd times, how many molecules of ammonia are produced? 2 times that number. That's right. So 2 times Avogadro's number. So what is the molar ratio? This is going to be 1 times that reaction. This is 3 times that number. This is 2 times that number. The ratio is still going to be what? 1 to 3 to 2. So when we look at this chemical, that's why we can say that these coefficients right here are equivalent to a mole. So here I would say 1 mole, because we know that 1 mole is 6.02 times 10 to the 23rd atoms, or molecules, or whatever. So if I do the reaction that many times, I'm still having the same ratio. So rather than having it as 1 atom of, or 1 molecule of nitrogen reacting with 3 molecules of hydrogen, now I can say 1 mole of nitrogen reacts with 3 moles of hydrogen gas to produce 2 moles of ammonia, and I still have that same ratio all the way throughout. All right, so that's why we can use the term 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. Any questions on that? A lot of it is, I mean, it's basically, you can see the ratio is the same. It's just we went from just 1 chemical reaction for 1 molecule, just 1 time, and we made it bigger. And so now rather than saying 1 of these things, now we can say 1 mole of these things, and we can look at these molar ratios between these molecules in the chemical reaction. All right. So when we look at stoichiometry, how much sodium, we want to know in grams, is required to make 42 grams of sodium hydroxide? So this is my question. And what is my given in this question? Yep, I have 42.0 grams of sodium hydroxide. So, and I'm given a chemical equation. And this chemical equation is where we start in all of these problems. Sorry, my cat jumped on my lap. There we go. Hi. So the very first thing we have to do is balance the chemical equation. Is this chemical equation balanced? Yes or no? No. So my sodium is balanced, okay? I have 1 oxygen. My oxygen looks balanced, but my hydrogens are not. So how should I go about doing this? I have an uneven number of hydrogens on my product side. So when I'm looking at these balancing chemical equations, if I have an odd number, it's best to try to get it so that there's an even number, right? So I'm going to put a 2 in front of this, and now I have 4 hydrogens. if I have 4 hydrogens, I need 4 hydrogens on my reactant side. I can put a 2 right here. So my hydrogens are balanced. I have 2 oxygens, 2 oxygens, 2 sodiums, 2 sodiums. So now I have a balanced chemical reaction. So when I have a balanced chemical reaction, remember my coefficient, I can replace that with the word mole. So in this chemical equation, I can say that I have 2 moles of sodium react with 2 moles of water to produce 2 moles of sodium hydroxide and 1 mole of hydrogen gas. All right, so my given is 42.0 grams of sodium hydroxide. Now, my very first thing I need to figure out though is if I'm given grams, what do I have to do? Convert to, everybody type it in the box, even those of you who are kind of dozing off. Yeah, I have to convert to moles. Thank you. To do that, I start with my given, 42.0 grams of sodium hydroxide. And I know that sodium hydroxide, 1 mole equals 40.0 grams of sodium hydroxide. Okay, that's my equivalency. I can write my conversion factor one of 2 ways. I can put moles on the top and grams on the bottom, or grams on the top and moles on the bottom. Which one do I want to do? If I have grams on the top here, I need grams on the bottom. So I would say 1 mole of sodium hydroxide is 40.0 grams. My grams are going to cancel out, and I'm left with how many moles of sodium hydroxide? Go ahead and do the math. Grab your calculator, and this one's an easy math problem. How many moles of sodium hydroxide do I have? Yep, 1.05. So I'm going to go back to my question here. How much sodium do I need? I'm looking for how much sodium do I need to make 42 grams of sodium hydroxide. Well, 42 grams of sodium hydroxide is 1.05 moles of sodium hydroxide. So this chemical reaction is a whole number reaction. It's 2 to 2 to 2 to 1. Those are my molar ratios. 2 moles of sodium to 2 moles of water to make 2 moles of sodium hydroxide and 1 mole of hydrogen gas. But I don't need 2 moles of sodium hydroxide. So I take this number here and I'm going to say 1.05 moles of sodium hydroxide. And I want to know the relationship between these two. I want to look at the molar ratio between sodium hydroxide and sodium, because that's what is being asked in this problem. So for every 2 moles of sodium hydroxide, I need 2 moles of sodium. Notice I'm keeping those coefficients the same, like right here. I'm not reducing it, okay? But my moles of sodium hydroxide are going to cancel out here, and I am left with 1.05 moles of sodium. Is that making sense? So I'm taking my grams, I'm going to moles, and then I'm looking at this molar ratio between the two things that I'm looking at. It says how much sodium is required to make this many grams of sodium hydroxide. So instead of using grams of sodium hydroxide, I converted that to moles. So now how much sodium is required to make 1.05 moles of sodium hydroxide? How much sodium is required to make 1.05 moles of sodium hydroxide? Well, then I take that 1.50 moles of sodium hydroxide and I look at the molar ratio between sodium and sodium hydroxide. And it really is a 1-to-1 ratio if I were to reduce it, but I'm keeping my coefficients, my moles, in their non-reduced state, okay, to get the most accurate answer. And I get 1.05 moles of sodium. Am I done yet? I'm at 1.5 moles of sodium. Now I know how much sodium I need. But the problem is asking for grams. So I need to convert 1.05 moles of sodium. And we know that 1 mole of sodium is how many grams? How do I find that out? I go to my periodic table and I say, how many grams are in 1 mole of sodium? Look at your periodic table and you guys put that in. Put that in the discussion. Good job, Lexi. Eli, good. Malachi, good. So 22.9, thank you, 9 grams. Well, my moles of sodium are going to cancel out, and I'm left with that number, 22.99. Grab your calculator and multiply it by 1.05. That is 24.14 grams. Now, that's 4 significant figures. I only have 3 significant figures that I can use. So my answer will be 24.1 grams of sodium. So how much sodium in grams is required to make 42 grams of sodium hydroxide? I need 24 grams of it. Okay. So you guys are, looking at this and you're going, okay, maybe that makes a little bit of sense. If it doesn't make sense, first off, that's okay. This is hard. We're taking a lot of math and running through all these numbers and scenarios and stuff. But if you just follow the process, it's really easy. Okay. In that, it's like, okay, I don't know what to do, where to start, but we can go through the process and determine what we used. Okay. Let's see. Everything is, yeah. Where are we at here? Let's do one more. I'm wondering if I have an easier one. Yeah, no, this is the last one. How many grams of nitrogen oxide can be produced when 12.5 grams of oxygen react with nitrogen gas? So here we have this problem, and we're given a whole bunch of information. How many grams can be produced when we have so many grams of oxygen reacting with nitrogen gas? So the very first thing we have to do is read that and say, what is the actual chemical reaction that we're looking at? All right, so the chemical reaction is oxygen plus nitrogen produces nitrogen oxide. All right, that's pretty straightforward. Then I have to say, is it balanced? Once I get that chemical reaction, I look at is it balanced? And the question answer is no. How do I balance it? I would need to have two nitrogens here, one oxygen and one nitrogen. That one's pretty straightforward. So what are my molar ratios in this problem? If I were to look here, molar ratio between these right here and this right here. So molar ratio, I have 1 mole of oxygen to 1 mole of nitrogen. I have 1 mole of oxygen to 2 moles of nitrogen oxide. And then that third one is going to be 1 mole of nitrogen to 2 moles of nitrogen oxide. Those are my 3 molar ratios that I can use in this chemical reaction. All right. What else do I know? I have 12.5 grams of oxygen. All right. Well, what do I do when I have grams? I convert to, go ahead and type it in. Here we go. I convert to moles. You're going to hear me say that probably 1,000 times. I don't know if anybody has like a thumb clicker, but for the rest of the second semester, if somebody wants to keep track of me, I'm like, do the math and convert to moles. Okay, those are the things I'm going to be in my sleep. That's right. So here I'm going to start with my given. I'm going to say 12.5 grams of oxygen, and I need to get it to my mole, 1 mole, and 1 mole of oxygen. Look at the type of oxygen I have there. That is O2. Okay, so I'm not looking at 1 oxygen atom there. I'm looking at 2 oxygen atoms. So 1 mole of diatomic oxygen is not going to be 16 grams. It's going to be 32.00 grams. Fair enough? Everybody understand that? Okay, so how many moles of diatomic oxygen do I have? 12.5 divided by 32. Grab the calculator, we do the math. Click. How many moles? .39. Okay, 0.391. So there is I have 0.391 moles of oxygen reacting with, let's see here. This is a 1 to 1 to 2 in a balanced chemical reaction. So how many grams of nitrogen oxide can produce when 12.5 grams of oxygen react with nitrogen gas? It doesn't tell us how much nitrogen gas we have. And what I want you guys to recognize is when it doesn't tell you how much you have, that means that there's going to be enough of it. All right. So if I have 0.391 grams of oxygen reacting, how many moles of nitrogen will I have reacting? It's a 1-to-1 ratio. Yeah, I'll have 0.391. Okay. And if I have 0.391 moles of oxygen reacting with 0.391 moles of nitrogen, how many moles of nitrogen oxide will I get? Yes, Jonathan, good. This is a 1-to-1 to 2 ratio. Now, I can set this up as a conversion line. I don't know. I don't know why my numbers are not lined up, but, and I can write 0.391 moles of oxygen, and I can say 1 mole of oxygen to 2 moles of nitrogen oxide, and that's going to give us 0.782, if I did my math right, moles of nitrogen oxide. Now I know how many moles of nitrogen oxide I have, but the problem is asking how many grams. Well, if I can go from grams to moles, I can also go from moles back to grams. And to go from moles to grams and grams to moles, I need to know the molar mass. Okay, so I write 0.782 moles of nitrogen oxide and I would write 1 mole of nitrogen oxide is how many grams? I'm given that up here, 30.01. So how many grams of nitrogen oxide can be produced when 12.5 grams of oxygen react with nitrogen gas? Do the math. Click. There's another one. Grab your calculator. 0.78125 if you're carrying out your calculation times 30.01. How many grams is that? Here we go. What is it? 23.445. All right. We are limited to 3 significant figures, so this is going to be 23.4 grams of nitrogen oxide. Now, if we rounded, like right here, I rounded this number in the middle of my calculation. When you are rounding in the middle of your calculation and you start dropping significant figures, it's going to, again, like if you're, just going 5 miles and you're 1 degree off, you don't get too far off. But the further the distance, the more calculations you do, the more rounding you do during the process, the further your number is going to be away from the actual number. Okay, so make sure you keep all those significant figures until the end, and then you do your rounding. Okay, so that is stoichiometry. There's not a lot of, the only stoichiometry that you have on the final test is what we see here on the semester review worksheet. Okay, so let's take, I'm not going to worry about my review specifically. Let me take 5 minutes of questions before we head over to our Christmas game. All right, so let's look at this. And are there any questions that you guys want to go through on the semester review test? And Eli, 23.467 would round to 23.5. If you guys put an answer of 23.4 or 23.5 and you have the right, just had a bug fly into my ear, and you have the right significant figures, I'm not going to mark you wrong. But if you're really far off, then I will mark you off like a quarter or a half a point saying something happened in your calculation. Okay. Here we go. So Any questions that you guys want to go over? Do you guys want to go over a unit conversion, density, significant figures? Just one Lewis structure, okay? So let's go here. Naming these as ionic, covalent, or polyatomic. Let me just clarify this. Like if you were doing silicon tetraiodide, you're going to write the formula there. So the formula would be SiI for silicon tetraiodide. This one, copper selenide, you know that copper has a 1 after it, so this is going to be Cu plus. Selenide is Se2 minus, so this would be Cu2 Se. All right, so you're really putting the formula right there. Okay, hopefully that clarified that. You do not need to put in every element here. This one, label 1 would be halogens. So this would be your halogen right here. So halogens are in red. Your noble gases, we'll just do in green. Here's your noble gases right here. So just write that in. You know, you don't need to put all the different elements in. If it tells you to put the element in, right there, put those ones in. All right. Oxidation state, what are the charge of the ions? So tin 4 right there. This would be SN 4 plus, okay, because that Roman numeral is telling you what the ionic charge is. Are these questions similar? Yes. And this is going to help you with the test. Okay, but you cannot use this worksheet on the test. You can have your book open, but I don't want any other papers around you when you're taking your test. Okay, but as soon as you get this done, I'm going to send you the answer key so that you can check all your answers on this worksheet so that you can make sure that you understand whether or not you did the worksheet correctly. Okay. Remember, protons in a neutral atom, your protons equal your electrons. So atomic number, protons would be 41. Atomic number, these ones equal each other. In a neutral atom, your protons equal your electrons. So in this case, if I have 41 protons and 35 electrons, what is my charge on the atom going to be? You have to look at the difference here. I have 41 more plus charges than I have 35 negative charges. So this is going to be plus 6 right there. Okay, so make sure that if these are equal, your charge equals 0. If the number of protons does not equal the number of electrons, you have to look at the number of protons and say, well, do I have more positive or do I have more negative? Okay, so make sure you pay attention to that. Lewis structure, because Jonathan asked, we have carbon, 2 fluorines, and 2 hydrogens. So if I were to draw this out, I'm going to say, well, I have a single atom, carbon, usually goes in the center. Around it, I'm going to put my fluorines and my hydrogens. Okay. Now, how many valence electrons do I have? I have 1 carbon is 6 electrons. My fluorines, again, valence electrons, I have 7 times 2. And hydrogens, I have 1 times 2. So total valence electrons are 6 plus 14 is 20 plus 2 is I have 22 valence electrons. Okay, when I have 22 valence electrons, I need to put those around in the atom. First and foremost, I'm going to start with these ones because I have bonding. These are all bonding atoms, right? So I have to have at least one bond between them all. So I've used how many electrons there? I've used 8. Now we know hydrogen cannot receive any more electrons. So my I have the rest of them are going to go on these on the fluorine. So 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I think I've 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Did I do that right? Help me with my math. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Did I do my math right? It's saying I need 2 more electrons, right? Carbon doesn't have 6, does it? Carbon has 4. It's in a group 4 element. So this is only 20. See? Even I make mistakes. So 20 valence electrons, that's what it's going to look like. So how many valence electrons total? 20. How many bonding pairs do I have? I have 4 bonding pairs. 1, 2, 3, 4. This word electron configuration, this should say geometry. Okay, so your electron geometry rather than electron configuration. Sorry that that's confusing, but that's the same on all of these. So cross out the word configuration because this is electron geometry. Does that make more sense? And so the electron, there's 0 lone pairs on this because we're only looking at the center atom. So the electron geometry is tetrahedral. The shape is also tetrahedral. And is this polar or nonpolar? Well, the fluorines are pulling this way and the hydrogens are pulling this way. This is, I believe, a polar molecule because we don't know if it could easily look like this. Okay, we don't know that the hydrogens are right next to each other or opposite of each other. So in this case, the fluorines are pulling, out in one direction, and the hydrogens are pulling out in another direction, and it's unequal. So this is going to be a polar molecule. All right. So again, valence electrons, bonding pairs, and lone pairs are only on the center atoms. So only look at the center atom for these ones. If there's, a chlorine out here or a fluorine, all of these lone pairs, don't put those into the lone pair number. All right, and then we have types of reactions and balancing. This is taking this one right here. When dissolved, you're going to take the words and you're going to make sure to put the phases in and balance those. We have a little bit of molar mass, molecules and moles. This is kind of what we were just doing today, moles to grams. Atoms, need to take into account Avogadro's number, and moles. Moles and molecules, that's going to be an Avogadro's number also. Mass and moles, you need to figure out molar mass. Okay, almost done, and then we'll jump over. Again, when you're reading graduated cylinders, remember you take your known number. Let's say this is 3. Let's see, 1, and then you make your guess. So 3.15, would be an okay guess on this one, because you always take your known and then you add your guess. Okay. Isotopes, this one, a lot of people keep messing up on this one. You need to take into account the percent abundance in your equation. So go back and review your notes on that if you need to, but you need to take the mass times the percent abundance, your mass times the percent abundance, or whatever that mass is right there. Right here. And your mass times percent abundance. And that's going to help you determine what the average atomic mass is. Okay. Again, more reading, some conversions. And then last is those molar ratios and a complete combustion reaction. And you're going to list out the molar ratios. Hint, there are 5, I think, on this one. So make sure you get all 5 molar ratios here. And once you get those, you start with your given here, and then you use your ratios to determine the moles of carbon dioxide. And then this one gives you a hint. All right, that is your semester worksheet. If you are close to being done with it, great. As soon as you submit it, I will send you the answer key, and your test is due Monday. Let's jump over to the breakout room. And I am going to just remove these really quick. Sometimes you have to start from fresh or it gives you a weird room. So I'm going to just add more breakout rooms here. We'll do one. How many do we have? We have 12 people. We'll do 3 breakout rooms. Okay. And you guys are going to, for the last 10 minutes of class, if you guys want to come on mic and on video in your rooms, I'll come and visit each one of the rooms. You guys can solve the riddles first, or if you want, you can solve the why is Santa afraid of getting stuck in the chimney? And there's a periodic table available. Okay. Oh, shoot. They're in the breakout. Can you go see? I can't. They just don't come on mic. Why? I don't know. I did. Get back to chat. All right, we're back in here in the main room. Is everybody back here? Can everybody hear me? All right, so why is Santa afraid of getting stuck in the chimney? Did anybody get that? He's fat. He's claustrophobic, yes. Thanks, Anna. And then did you guys who got all the riddles? Pretty straightforward and pretty easy. Good job. So it's okay, you guys. It was just more to next time you guys feel free to come on mic and if you guys want to do that. Um, Otherwise, you guys are good to go. Merry Christmas, Happy New Year. We will see you in 2026. I believe it's January like 5th, I think, is when we're supposed to come back. So I just pray that you guys have a good holiday season. Stay healthy. Don't eat too many cookies, too much sugar, because it's just going to make you more sick. We're in the sick season. There's no such thing as flu where everybody's just sick from too much sugar, right? Um, yep, happy holidays. And I just pray that you guys have some wonderful downtime. Take that test by Monday, and I'll work on grading over the next week or so to catch up. And as soon as you turn in your worksheet review, test review, I will send you the answer key. We'll see you guys later. Bye, guys.